Good morning. We're going to look at something called trigonometric substitution. It's a technique, a very useful technique to solve certain types of integrals. Okay, so here's an idea. If you had something like this, the square root of x squared minus a squared, if you're trying to integrate something like this, it's very difficult because, well, U-substitution doesn't work. But what I can do is, if I have, well, actually, for my illustration, sorry, let me flip this around. Say a squared minus x squared, I can do a clever substitution like this. If I had something like this, a squared sine squared theta, okay, then I could take out the a squared and have 1 minus sine squared. And then remember that I have a trig identity that allows me to replace 1 minus sine squared with cosine squared. So now I get square root of a squared cosine squared, which would be a times the absolute value of cosine. Okay, so if I can make this clever substitution where I let x be a sine theta, then actually I can reduce the square root to just a trig function. And if I'm careful about my angle that I let my substitution take on, then I can actually drop the absolute value. And now it's, instead of integrating square root of a squared minus x squared, I'm just integrating the a cosine theta plus times its derivative, which would be a very easy thing to do. Okay, so that's the idea we're going to use today with trigonometric substitution. It will have three cases. So this is the first case, is when I have a square root of a squared minus x squared. And I'll go ahead and write those out, and then we'll just talk more about what's going on later on. Okay, so if I had a squared minus x squared, what I want to do then is I'm going to let x be a sine theta. And then there's kind of a funny restriction, because we don't actually ever deal with theta unless maybe we're dealing with a definite integral. But I restrict my angle to be from negative pi over 2 to positive pi over 2. And the reason I'm doing that, that's quadrant 4 and 1. It's so that I can drop the absolute value here at the absolute value of cosine. And when I do this, the identity that I'm going to use to help me reduce the square root is the 1 minus sine squared theta equals cosine squared theta, which is the Pythagorean identity just rearranged algebraically, right? So if I'm making this a table, so here's my expression. That's what I start with. Here's my substitution. And then here's the identity that kind of makes this substitution useful. And what we'll see is you can actually draw a triangle. I mean, we're doing trigonometry, right? So if you draw a triangle, it can make some of this stuff even more clear than just memorizing this table, which is what I recommend. I recommend that you understand how to build a triangle, because to be honest, sometimes I forget just by looking at, like, for example, the square root of a squared minus x squared, I forget that I need to let x be a sine. But if I can do the triangle, build the triangle myself, it makes it a lot easier on me. Alright, so if I have a square root of a squared plus x squared, your substitution you're going to use there is tangent. And your restriction on the angle is going to be the same, except we don't allow it to be negative pi over 2 to pi over 2. And again, that's kind of a technicality. It's just so that when you have the square root and you want to drop the square root, you still have a positive value. And what we're going to use here is the trig identity 1 plus tangent squared equals secant squared. So the square root is actually going to end up being a secant expression. And then lastly, if I have x squared minus a squared, okay, what I'm going to allow for my substitution to be this time is a secant theta. And again, so my square root reduces to a positive value. I have to restrict theta to be in quadrant 1 or in quadrant 3. All right, now why on earth would that be? Because I'm letting x be a secant theta, and then I'm using the trig identity that secant squared minus 1 equals tangent squared. So my square root is going to simplify to a tangent, and so I need tangent to be positive, so that's why I do first and third quadrant. All right, now don't worry too much about the angle part. That's not really part of what we need to consider here. what we need to consider mostly, and that's just kind of a technicality to make it more precise, what we really need to consider though is how do we make these substitutions to integrate. And I'm going to show you that through several examples today. Let's look at the first one, example 1. We're going to integrate the square root of 9 minus x squared over x squared dx. Okay, so now notice here, if I just gave you this as an integral, not knowing what section of the textbook we're in, what would you try? First, you might try a U-substitution. U-substitution is not going to work. We have these x squareds. We never have a 2x anywhere. U-substitution is not going to work. You might want to try integration by parts. That may work eventually. It's going to get a lot more complicated though. The fact that this has this square root of 9 minus x squared and U-substitution doesn't work, it makes me think I need to try this trig substitution idea. Now, I said you could draw a triangle and figure it out from there. Let me show you what I'm talking about. So let's put an angle here. And what I need to recognize is that I have a something squared minus something squared. If that's the case, I can build a triangle like this. The square root of 9 minus x squared is one side of that triangle. If that's the case, the other sides are going to be x and 3. And if you're wondering what on earth is that talking about, well look, x squared plus the square root of 9 minus x squared squared equals 3 squared. That's the Pythagorean theorem. It satisfies Pythagorean theorem. That's x squared 9 minus x squared equals 9, and you can see that that's a true statement. So that's how we build this triangle according to Pythagorean theorem. And the fact that in the square root I had the 9 first minus something, 9 minus, that told me that the hypotenuse was going to be the 3, the other side was going to be the x, and so this square root was the third side. Okay, so that's how I built this triangle. Now, the reason I say this is helpful is because look, according to this triangle, opposite over adjacent, so sine theta is opposite over adjacent, right? And that's exactly how I get my substitution that x equals 3 sine theta. Now, according to our table, look, I said that if you have a square root of a squared minus x squared expression, I need to let x be a sine theta. Okay, so I could memorize it, or I could just simply use the triangle and see here that opposite over adjacent would be x over 3, sine of theta is x over 3, so x then is 3 sine theta. Okay, now if that's the case, what about dx? Well, take the derivative of 3 sine theta, you get 3 cosine theta d theta. Okay, and also notice, let's take this, so let's say that's part 1. Part 2 then also is that the square root of 9 minus x squared is going to be the same thing. Now, according to our substitution, 9 minus 3 sine theta squared, which is the square root of 9 minus 9 sine squared theta. Okay, and I can take out the 9 and have a 1 minus sine squared theta there in square root. And according to trigonometry, remember 1 minus sine squared is the same as cosine squared. So we get 3 absolute value of cosine, and this is why we restrict our angle in our substitution to be in quadrants 4 and 1. So now I know that cosine will always be positive there. So this 9 minus x squared just ends up being 3 cosine theta. Okay. Now also I want to point out here that look, if I had just used the triangle, I could have seen adjacent over hypotenuse, cosine theta equals the square root of 9 minus x squared, that's the adjacent side, over the hypotenuse, and look what I get. I get that the 9 minus the square root of 9 minus x squared is the same thing as 3 cosine theta, which is what I did with all this algebraic manipulation here. So I can either use the identity, which is what we did here. This is the identity approach. Or I could use the triangle approach. Okay? I can use either one to figure out how this square root of 9 minus x squared reduces down to 3 cosine theta. And so now I'm ready to approach this integral. So I had the integral of the square root of 9 minus x squared over x squared d theta. I'm sorry, got a little ahead of myself there, dx. And now I'm going to replace this with, well, let's see, the 9 minus x squared square root is actually the same thing as 3 cosine theta, right? We just said that. The x squared, well, x is 3 sine theta, so that's going to be 3 sine theta quantity squared. And then the derivative, the dx, is the 3 cosine theta d theta. Okay, so I'm making these substitutions one at a time here. So the square root of 9 minus x squared becomes the 3 cosine theta. I'll try to color code this. The x squared becomes the 3 sine theta squared. And then let's see, I need another color. The dx is the 3 cosine theta d theta. And now where I could not integrate this square root of 9 minus x squared over x squared dx, I can integrate this other expression, because look what happens. I end up with a 9 cosine squared over 9 sine squared d theta. Okay, so I get the integral of cotangent squared d theta. Okay, and I'm going to use a trig identity here that, remember, 1 plus cotangent squared equals cosecant squared. So if I solve that for cotangent squared, I get cosecant squared theta minus 1 is the same thing as cotangent squared. Okay, so if you're trying to remember the Pythagorean identity that I use there, we have 3 Pythagorean identities. One of them, probably the one that's forgotten the most, is that cotangent squared plus 1 equals cosecant squared. Okay, and that's what I used here. And I can integrate then, because the integral of cosecant squared is negative cotangent, and the integral of 1 is theta, and of course I have a plus c. Alright, so there is my integral in terms of theta, but what I want to do is get it back into x's. I want to get it back into an algebraic statement, okay? Alright, so let's convert theta back into x. And so how do I get this expression? Alright, so let me write what I have so far. I have square root of 9 minus x squared over x squared dx equals negative cotangent theta minus theta plus c. And I need to figure out a way to get that back into my x language. And I can do that again using my triangle. Okay, so cotangent, well, let's see, tangent is opposite over adjacent, right? Opposite over adjacent would be x over the square root of 9 minus x squared. Cotangent is reciprocal of that. It's adjacent over opposite. So cotangent then is negative adjacent, which would be the square root of 9 minus x squared, over opposite, which is x. So that's how I figure out my cotangent expression. All right, now what about just theta itself? Well, remember, theta came from up here. Sine theta is x over 3. So that means then that, I'll write it here as a note, since sine theta equals x over 3, theta equals the inverse sine of x over 3. And remember, we restricted theta to be quadrant 4 to quadrant 1, so that is consistent with inverse sine. So it works out for us. We get inverse sine, sine inverse of x minus 3, and then we have our constant plus c. And finally, there is my integral. Whew. Okay, is that confusing? Maybe. Let me go back through it again real quickly. We'll do several examples, okay? So the idea is, again, you build this triangle, and what I did is I recognized that this was an expression of Pythagorean theorem under the square root. So let one side be the square root of 9 minus x squared, and then I have x and 3 as my other two sides of this triangle. They satisfy Pythagorean theorem. And then I can replace x now with this expression 3 sine theta because of opposite over hypotenuse definition for sine. Sine theta is x over 3, which then allows me to find dx just by using chain rule. And then I can also replace the 9 minus x squared under square root, either through an identity or by recognizing for my triangle that cosine is adjacent over hypotenuse, and so that this 9 minus x squared is going to solve down to 3 cosine theta. From that point, I can take my original integral and just replace the pieces I found. Square root of 9 minus x squared is 3 cosine, x is 3 sine, dx is 3 cosine d theta. From there, I just have to do some relatively simple integration, remembering the integral of cotangent squared, having to use a Pythagorean identity to change it out, and then integrating cosecant squared, remembering that that's the antiderivative of cosecant squared is negative cotangent theta, and then finally going back from theta to x world, again using the triangle. So you see, if you use the triangle instead of simply memorizing the table, you can reconstruct everything you need. Alright, so let's do some more examples here. For those of you taking my Cal 2 class right now, this may look familiar. Find the area of the ellipse x squared over a squared plus y squared over b squared equals 1. I believe this was a take-home test question, and I had actually omitted it because you didn't have the tools to integrate this yet. Okay, but now we do. Alright, so here's the idea. We have this ellipse centered at 0, and it's going out from a to negative a here, and b to negative b in the y direction. Alright, and we want to find the area. Now what we're actually going to do here is find just one part of this, because this is symmetrical, and then just multiply it by 4. Okay, so the first thing we want to do actually is get this solved for y. So if you do some algebra here, you can get y equals plus or minus b over a, the square root of a squared minus x squared. Okay, so I'm just going to hit the algebra button for the sake of time. I believe you can all handle that. And I'm just going to consider the positive part here because I just want the positive, this first quadrant intersection of this ellipse. What we're looking for here then is that 1/4 of the total area, which is just that one quadrant, is going to be the integral from 0 to a positive b over a square root of a squared minus x squared dx. Okay, that's what I'm finding there. Alright, and can I integrate this square root of a squared minus x squared? Well, I can't use U-Substitution. So since it has a square root, I'm going to recognize that we should draw a triangle and do a trigonometric substitution. Okay, so let's think. If I have an a squared minus x squared, that means my hypotenuse is the first term, that's the a. The opposite side, or the one side of this triangle is x, and that means the third side then is going to have to be the square root of x squared minus a squared. This is just like the one we just did. Alright, so what I'm going to do now is let, well look, sine of theta is opposite of hypotenuse is x over a, so that means then that x equals a sine theta, which also means that dx is a cosine theta. And I also recognize that cosine theta, let's go ahead and say this, is adjacent over hypotenuse, so that's the square root of a squared minus x squared over a. So then this square root, which was causing the problem, is just actually the same thing as a times cosine theta. Alright, so now that I have that, I can take my integral. I can say that's 1/4 a is going from 0 to a, 1/4 capital A is going 0 to little a, square root of a squared minus x squared dx is actually the same thing now as the integral from 0 to a. And let's be careful here. Let's say here the integral from x going from 0 to x going a, b over a. This square root is actually the same thing as a cosine theta, And then dx is actually a cosine theta d theta. Okay, so there is your, this came from this square root, and all this came from the dx. All right, so that's my integral at this point. Okay, and now also notice that if I'm trying to do a U-substitution, or not a U-substitution, a trigonometric substitution, instead of going from 0 to a, what am I doing? My rotation is going from 0 to pi over 2, right? It's just that first quadrant. So I can write this completely then as 0 to pi over 2, b over a squared cosine squared d theta. All right, and one of the a's cancel out, right? So I actually have just b times a cosine squared d theta like that. Okay, now how do you integrate a cosine squared? That's a good question. We did that in the last section. That's where you have to remember what we call the reduction formula. You have to remember that cosine squared theta is the same thing as 1 minus 2 cosine of theta over 2. Okay, that's the route you have to go here. That's not correct either. 1 plus cosine 2 theta. Sorry. All right, so and all that's doing is rearranging the double angle identity for cosine, one of the double angle identities for cosine. So here I end up with, and I'm missing something. Cosine squared, yes, sorry, times 1/2. Okay, so I have then 0 to pi over 2, ba over 2, 1 plus 2 cosine 2 theta d theta. Okay, and from there we can do a U-substitution. We're going to end up with this once you do your integration, and we've done integrals like this before. So you can let u be 2 theta, and you have a 1/2. All right, so you end up with this after you do your integration. All right, you're going to end up with that the area, so 1/4 a is going to be 2 AB, let's see, actually AB over 2 theta plus 1/2 cosine, I'm sorry, the integral of cosine sine 2 theta going from 0 to pi over 2. Okay? All right, and so here then a, if you multiply both sides by both sides of this equation by 4, you get 2ab theta plus 1/2 sine 2 theta going from 0 to pi over 2. Now here I don't really have to go back to the x world, the expressions in algebra. And why is that? Because it's a definite integral. We've done all our conversions already. And notice that if I plug in pi over 2 or 0 into the sine expression, I'm going to get 0 both times. So this ends up being 2ab times pi over 2 plus 0 minus 0. And so I just get, what is that? AB pi, or pi AB, however you want to write that. And that is the total area of the ellipse. I hope that makes sense. Now, look, if your A and B are the same thing, what happens? You have a circle, and we know the area of the circle is going to be what? Pi r squared, r being the distance of A. And so look, if A and B are the same, that's exactly what you get, pi a squared. This is consistent with the area of a circle, just a little bit more general. All right, let's try another one. So we've done 2 examples now where we do a substitution with sine. How about this one? So integrate 1 over x squared, the square root of x squared plus 4 dx. Hopefully you see that a U-substitution will not work on this. So I'm going to turn to a trigonometric substitution because I have this square root here. And this time though, notice that it's a plus. So that tells me that in Pythagorean theorem, this is my hypotenuse. My hypotenuse is the square root of x squared plus 4. And that's going to force then my other sides to be x and 4. Okay? Not x and 4, x and 2. And actually I want to arrange it a special way because I want, well, we'll see. Okay, so now if I'm going to try to figure out how to solve x out of this triangle, Well, look, what if I do opposite over adjacent? If I say, what is that? Tangent theta equals opposite over adjacent. And that's why I swapped the order of x and 2, because I wanted it to be a tangent situation. So if tangent is x over 2, in other words, x equals 2 tangent theta, dx then is going to be what? 2 times the derivative tangent, which is secant squared. All right. And then we could also see that what about this x squared plus 4? So if I have hypotenuse over adjacent, is that not the reciprocal of adjacent over hypotenuse? That would be secant is hypotenuse over adjacent, which says then that the square root of x squared plus 4 is 2 secant theta. All right. It's funny how we usually want to pair tangent and cotangent in trigonometry, but in calculus, time and time again, it's tangent and secant, right? All right, so here, then we can replace my integration now with, well, let's see, x is tangent. So I have 2 tangent theta quantity squared. The square root of x squared plus 4 was secant. So I have 2 secant theta. And then my dx is 2 secant squared theta d theta. And I needed to write a d theta up here in my substitution. All right, so now when I simplify this a little bit, let's see, what do we get? Well, notice that the secant squared in the numerator and the denominator can cancel, as well as a 2. So I end up with d theta. Well, actually, sorry. I end up with a secant theta d theta in the numerator, and the denominator ends up with 4 tangent squared theta, right? So what's going on here? One of my secants cancel out, and then a 2 cancels out as well. So I'm left with secant theta d theta over 4 tangent squared theta. How does this reduce? Well, let's do some trig identity manipulation. Hopefully we can get this down. So what I want to do, and at first you might think that looks like a U-substitution, right? You let U be tangent, but then du is secant squared, not just secant. So a U-substitution is not going to work here. So what I'm going to do here is I'm going to rewrite everything in terms of sine and cosine, and hopefully that will help us clear this up. So remember, secant is a reciprocal of cosine. So that's 1 over cosine theta times the reciprocal of tangent squared, and that could be, let me write it like this, 1 over sine squared cosine squared, and dividing by a fraction, same as multiplying by reciprocal. So that's 1 over cosine theta equals cosine squared over sine squared. And now hopefully you can see that that reduces down to cosine over sine squared. All right, so now my integral here is going to be 1/4, taking out the 1/4. All of this secant and tangent squared is the same thing as cosine theta over sine squared theta d theta. Being able to manipulate trig identities is a very useful tool, and once you get pretty good at it, it's kind of fun, right? It's like a puzzle. How could I reduce this? And one tip is, if you're confused on how to do it, try to get everything in terms of sine and cosine. For some reason, when you get into sine and cosine, it becomes a lot more familiar to us, and we can see it a lot more. And in particular here now, if I let u, so let's let u be what? Sine theta? Then du is going to be the derivative of that, which is cosine theta d theta. And this ends up becoming a situation where we have 1/4 1 over u squared du, which is something we can integrate. Okay, so just to recap, we started with x's, then we converted to thetas. Well, actually, we started with x's, we turned it to not only thetas, secants, and tangents, and then we had to turn it into sines and cosines, and now we've turned it into u's. So once we get this integral, we're going to have to work all the way back through the thetas back to the x's, okay? But anyway, I know how to integrate 1 over u squared. That's u to the negative 2 power. So that's going to be negative 1/4 u to the negative 1 plus c, right? So that's going to be negative 1/4. Well, let's go. What was u? U was sine theta. So that's 1 over sine theta plus c, right? Which is the same thing as negative 1/4 cosecant theta plus c. So that's where we are right now, okay? Now, and here we went from u back to theta. That's what we did here. Now we need to go from theta back to x. And how do we do that? With our triangle, okay? Be sure to draw a triangle with these, even if you're tempted just to memorize the table, but you can be an engineer. If you draw the triangle, you can figure it out, because what we need now is what? A cosecant. So I go back to my triangle, and I think, okay, cosecant is a reciprocal of sine. Sine is opposite over hypotenuse. So cosecant is hypotenuse over opposite. That's going to be the square root of x squared plus 4 over x. So here I end up with negative 1/4. What did I say? The square root of x squared plus 4 over x. That's how you find your cosecant value plus c. And to write it a little more succinctly, square root of x squared plus 4 over 4x plus c. And what's amazing about this is that I would not have guessed the antiderivative of this expression to be what we ended up with. Right, this negative square root of x squared plus 4 over 4x, that would have been very difficult to guess. This trig identity idea, going through the triangle, allows us to kind of sidestep the difficulty because the trigonometry is fairly familiar to us, and then we can work our way back to a more complex algebraic statement. It's a really cool idea. All right, and let's just work a few more, okay? So there are plenty of examples here, and I want to make sure you kind of see everything. So we're just going to keep going. Example 4, this time we want to integrate x over the square root of x squared plus 4 dx. All right, now, so we want to use trig substitution, right? But first, remember, don't just get locked into the context of where we are in the book, which is a temptation. We're thinking we're in trig substitution land, so we're going to do trig substitution. But notice here, if I let u be x squared plus 4, then what's du? 2x dx. I can apply a U-substitution here. This is 1/2 du is x dx. So then my integral becomes, well, the x dx is just 1/2 du. So I get 1/2 du over square root of u. That's something I can integrate pretty easily, right? So that's u to the negative 1/2 power. So what do? You raise the power by 1, and then divide by that power. You're going to end up with a square root of u plus c, which means this is just the square root of x squared plus 4 plus c. We didn't need to do a trig substitution. So you need to always double check or go through the process, honor the process, start out seeing if you could do a U substitution first. All right, let's look at example 5. And let's see if we need to use a U substitution or not. Okay, so here's dx over the square root of x squared minus a squared. And here they specify, look, where a is greater than 0, okay? All right, now U substitution won't work, so we're definitely have to move something else, and I recommend going to the triangle because of that square root. And think to yourself, what side of this triangle, or this x squared minus a squared, that's not going to be the hypotenuse, right? The long side's the hypotenuse, so this time x is the hypotenuse. And then I'm going to set it up like this, x squared minus a squared, square root there, and then a right here with my right triangle. And now look, in doing so, let's see, hypotenuse over adjacent, that is secant. Secant theta is x over a, okay, which means x is a secant theta, and dx is going to be a secant theta tangent theta. Okay, it also tells me that, let's see, the square root of x squared minus a squared, if I'm trying to substitute that, I can say opposite over adjacent, tangent theta equals the square root of x squared minus a squared over a, which tells me then that expression, x squared minus a squared, equals a tangent theta. And don't forget, if you really wanted to, you could always go and plug in a secant squared, or a secant n for x squared here, and then evaluate, and it'll reduce down again to a tangent theta. I like using the triangle more, which is fine if you want to. All right, so now then my integral becomes what? Let's see. Well, I changed dx to a secant theta tangent theta d theta. I left out the d theta again. And then in my denominator, that square root of x squared minus a squared is what? A tangent theta. So then what happens? My tangents cancel out. I'm just looking at the integral of secant theta d theta. The a cancels out as well. And remember we did that last time. The trick to this one, let me go over it again because I just think it's so cool. You multiply by secant theta plus tangent theta divided by secant theta plus tangent theta, like that. And then when you distribute here, you get secant squared plus secant tangent. You can do U-Substitution, and you end up with ln of secant theta plus tangent theta plus c. So you let your U-Substitution be secant theta plus tangent theta. All right, and you can find that in the last section if you want to review that. Okay, now from there we can't leave it like this, right? We got to get back to x world, but secant we already knew. Secant is x over a, and tangent is x squared minus a squared over a. So here we end up with ln x over a plus the square root of x squared minus a squared over a plus c. And remember, with logarithms we have this property. So first of all, let me bring this together. Look, we have a common denominator, right? So this is x plus square root of x squared minus a squared over a plus c. And remember, with logarithms we have a property that you can take the division and turn it into subtraction of logs. So if you have division in the inside the logarithm, you can pull that out as subtraction. So this is actually ln of x plus the square root of x squared minus a squared minus ln a. But remember, ln a is a constant. So I can bring all this together and just finally end up with ln x plus the square root of x squared minus a squared plus another constant. We can call it c1 if you want. A lot of times we just write plus c. It's like it just absorbs it because a constant plus a constant is still a constant, right? Okay, good. I hope that makes sense. Now, actually, this one had a second solution, so let me show you real quick because it deals with something that I think we like. So I'll write it in red real quick. Solution number 2 to this expression. What I could have done is I could have let x be a hyperbolic cosine t, cosh t. And the reason that that works is because remember that with hyperbolic functions, cosine squared minus hyperbolic sine squared equals 1. Okay? And so what happens then is that this x squared minus a squared turns into a squared times cosh squared x, we used t, didn't we? T minus 1, okay? And that is the same thing as a squared sinh squared t from our trig identity here. And then, so we end up with just a sinh t plus c. Not plus c, sorry. And then, so that becomes my substitution. So then my integral dx over this x squared minus a squared actually ends up becoming a sinh t dt, because that's my, we didn't find it, but dx would be the a sinh t dt over the x squared, which is a sinh t, like that. So we end up with the integral of dt, which is just going to be t plus c. And then we have to replace the t back with x's, And so that's going to be inverse of hyperbolic cosh x over a plus c. That is a second way to solve this. And if you remember when we looked at inverse hyperbolic cosine, we had a logarithmic expression for that. You could, because remember the definition of cosh comes from an exponential, right? Writing in exponentials. So these are actually equivalent statements. And we saw that with the inverse hyperbolic cosine in a previous section, okay? Now, more than likely, you're probably not going to write the solution to that. Maybe that's why I wrote it in all red. It almost looks like we're doing something wrong. We'll more than likely go with the trigonometric substitution instead of the hyperbolic trigonometric substitution, but isn't that cool that we could do that as well? It's pretty neat. All right, so I have two more examples we want to go over. I'll try to not linger too long. If you have questions on them, don't forget though, you can ask. I would be glad to look over it. All right, so example 6 here, we're going to integrate going from 0 to 3 root 3 over 2. And we have the expression x cubed over 4x squared plus 9 to the 3/2 power dx. This looks really tough. Okay, so what you have to remember is that 3/2, this is the same thing as saying 0, 3 root 3 over 2, x cubed over the square root of 4x squared plus 9 cubed, right? Because the 3/2, the 1/2 power means the square root, and then we're just cubing all of that. So this is actually a very similar situation to what we had already. We're going to draw a triangle again. Here we have theta, and the x squared here would give me one side of my triangle, and that's the hypotenuse, x squared plus 9, like that. And so then my opposite and adjacent sides are going to be 2x and 3. So then here I get tangent theta is 2x over 3, or x equals 3/2 tangent theta. All right, that's kind of the substitution we're working with. And dx is going to be 3/2 times the derivative of tangent theta, which is secant squared d theta. And also the square root of 4x squared plus 9 is going to be hypotenuse over adjacent secant theta equals that square root of 4x squared plus 9 over adjacent side, which is 3. So then my denominator there is just 3 secant theta. All right, so that's what we end up with. Hopefully by now this is getting a little bit more familiar on where we're finding this stuff. What we also need to do is, if we're going to convert over to thetas, since we have an indefinite integral, I mean, why don't we just go ahead and convert? So if I had 0 and 3 root 3 over 2, what happens when I plug those in for theta, okay? So if I'm plugging in 0 in for x, I get tangent theta equals 0. That's going to give me theta is 0. And if I plug in root 3 over 2 into 3 root 3 over 2 into 2/3 x, the 2/3 and the 3/2 cancel, so I get tangent theta equals root 3, and that happens at pi over 3, or 60 degrees. So now I can convert all of this into the integral 0 to pi over 3. Okay, x is 3/2 tangent, so I get 3/2 tangent cubed theta. The 3/2 is cubed as well. And in the denominator I have, let's see, we said, and I left out my dx again. I don't know why I've been doing that all day. Okay, so let's not forget the dx here. That's going to be another 3/2 secant squared theta d theta. And in the denominator I have this 4x squared plus 9, so it's going to be a 3 cubed secant cubed theta. There's a lot going on here, right? So if you take care of all these constants very carefully, you're going to end up with 3/16 integral of 0 to pi over 3, and you end up with tangent cubed over secant d theta. We can't use the U-substitution here, so you want to go to a trig identity, or go to sine and cosine world. So here we end up with sine cubed 3/16 0 to pi over 3, sine cubed theta over secant is the same thing as 1 over cosine. So I'll show you what I'm saying here. I have sine cubed over cosine cubed, that's the tangent, and then times the reciprocal of secant, which is going to be cosine theta, like that. Okay, and so we end up with, let's see if this makes sense to us. And I'm running out of room, so let me come up to, well, let me write it down here, then we'll jump to the top. You get 3/16 0 to pi over 3. One of the cosines cancels, so I have sine cubed theta over cosine squared d theta. How do I solve this? Well, remember from last time we could do this. You have the 3/16 0 to pi over 3. Let's pull out one sine. So I have sine theta d theta out here, and then I'm just left with sine squared over cosine squared. And now, remember when you have an odd power when you have these trig functions of raised to powers, and one of them's odd, so sine's odd, take out one sine, and now I can use a Pythagorean identity to reduce sine squared to 1 minus cosine squared, and then I can use a U-substitution. That's what we did last time. So let's go up to the top of our notes here, and let's finish that out. So here, we're going to let U be, well, actually, I left out a step. Okay, so here we have 3/16 0 to pi over 3, and I'm rewriting that sine squared as 1 minus cosine squared theta over cosine squared sine theta d theta. All that translates to that, and now I can let U be cosine theta, which means du is negative sine theta d theta, and so my integral now becomes negative 3/16 0 to pi over 3. Whoops, we should be careful. That's theta. We'll convert our thetas. We get 1 minus u squared over u squared du, like that. Okay, and to convert my u's, just let's see, if I have theta and u, if theta is 0, all right, cosine of 0 is 1, and if theta is pi over 3, okay, cosine of that would be 1/2. So here I have the integral of negative 3/16. We're going from then 1 to 1/2. All right, which seems backwards, right? So we can make this positive again. 3/16 1/2 to 1, 1 minus u squared over u squared du. We are going all over the place with this, right? That's great. This is exactly what we want, because this is good preparation. So how do you integrate that? Well, let's break it up into two integrals. Since we have a common denominator, that's going to be 1 over u squared du minus the integral of 1/2 to 1 of u squared over u squared du, which is just the integral of 1. Okay, so now we have 3/16. The integral of u squared is going to be, that's u to the negative 2 power, right? So that's going to be negative 1 u to the negative 1 going from 1/2 to 1 minus the integral of 1 is just u going from 1/2 to 1. Multiplying all that by 3/16. Just be really careful with the arithmetic here. Let's see, you should get something like this. 1/2 plus 2 minus 1 plus 1, and you end up with 3 over 32. There's a lot of room for error there. This is an interesting example, right? We had to go everywhere with this. Let's see. Let's look at it again. So we started out having to do um, an unusual trig substitution because we didn't just have x squared by itself, and so we ended up though with x being 3/2 tangent and the square root being 3 secant, and then we made our substitutions, our trig substitutions. Okay, we had to do some trig identities to simplify into something that we recognize. Then we had to do stuff from 7-2. We pulled out one sign so that we can make an appropriate U-substitution. So then we went from thetas to U. We had to convert again our limits going from theta to U. We also had to remember that if you want the smaller limit on the bottom, you might have to flip your integral and make it negative. That's what we did here. And then from there, we could just pull it apart and integrate separately. And we were very, very careful with our arithmetic, or at least the book was. I kind of followed some of the book's work on that last part. But we could integrate this and just be really careful with our steps, okay, as far as arithmetic. A lot of room for error there. That's a good question. I like that one. It made us think a little bit. All right, now let me show you one more that's also going to make us think a little bit. And just pay attention to this, okay? This is an important one. 3 minus 2x minus x squared dx. And when I'm looking at this, I don't see immediately how this is a trig substitution because I don't have my triangle set up. So what I'm going to do here is I'm going to take the 3 minus 2x minus x squared, and I'm going to have to do something called completing the square on this. All right, so here's what I'm going to do. I'm going to say 3 minus, that's the same thing as x squared plus 2x. Okay, so I factored out the negative and put the quadratic term first. And now remember, to complete the square, what you do is you take the linear term, the coefficient, you divide by 2, and then you square that. And then you're going to add it in. So I'm going to add it in and then subtract it immediately. Because if I add it and subtract, if I don't subtract it out, I have changed what I started with. Notice that when you cancel out as soon as you cancel out these ones, you go back to where you were. All right, so we haven't changed anything. We added in 0, but we added in 0 in a very clever way. And the reason this is clever is because x squared plus 2x plus 1 will factor as a complete square. Okay, so all I need to be able to do is take out the negative 1 outside of the parentheses, but everything in the parentheses is being multiplied by that negative 1. So follow this very carefully here. I have 3 minus, I can go ahead and factor that as x plus 1 quantity squared, and then when I take out the negative 1, that becomes a plus 1. So this ends up being 4 minus x plus 1 quantity squared. Completing the square is a very, very handy technique to have on hand. All right, so my integral then becomes x over 4 minus x plus 1 quantity squared dx. All right, now we are not going to actually have to use a trig substitution on this, I don't believe, at least not yet. What I can do here is, I don't like the x plus 1, so let's let u be x plus 1, which means since that's a linear substitution, I can say then that x is the same thing as u minus 1, and du is just the same thing as dx, right? So here my integral then becomes u minus 1 over the integral of the square root of 4 minus u squared du. Okay, now that's kind of our new starting point if you want to think about it. All right, so from here we are going to have to make a trig substitution, and just for the sake of time, I'm not going to draw out all the triangles. What you'll do is you'll end up with, let's see if you can figure this one out, 2 sine theta minus 1 over 2 cosine theta, and then my du is 2 cosine theta d theta. And why is that? Because here, from this expression, I know that I'm going to end up with x equals 2 sine theta. Okay, so draw a triangle. See if you can get that. All right, now, so finally, here, my cosines cancel out, and I'm just integrating 2 sine theta minus 1 d theta. So that's going to give me 2 cosine theta, negative 2 cosine theta, minus theta, plus c. And now I have to work backwards. And so the cosine theta from my substitution becomes negative square root of 4 minus u squared. The theta, I'm going to have to use a sine inverse. So I have sine inverse of theta over 2, u over 2 plus c. And now I convert finally back into x's. Remember, x was what? U minus 1. And in fact, though, the 4 minus u squared was originally what was under my denominator here. So that's the square root of 3 minus 2x, right? 3 minus 2x minus x squared minus sine inverse of what my u was. U was x plus 1 over 2 plus c. That is an awesome, awesome example. And it's really not anything new except that we had to remember to complete the square. So this is completing the square here, which is a big deal. All right, guys, we've done a lot. We've been on here for about an hour, and I think this is the first day in calculus we haven't had some sort of technical issue. So I'm sorry I ran a little long, but we are now through with everything that we're going to cover this semester. Trig substitution, it's a little weird, it takes some practice, but it's an incredible technique, and it's brilliant. If you have any questions on it, I'd be glad to help. Just take care, keep working hard, we're almost done. This is the last of the new material for this class. We'll see you guys. Let me know if you have any questions. Stay safe. I'll talk to you later.